Stars are whispering tales of old, planets spinning, stories bold. Life is dancing through the night, countless worlds in the starlight. Galaxies full of mystery, infinite in their history. Beyond our dreams and our sights, life blooms in the cosmic lights, dancing on the edge of space. Take me away, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Nebulas with colors bright, birth new wonders in the light. Comets trail their sparkling tears, life endures through the years. In the silence of the void, every heartbeat is enjoyed. From the depths and to the heights, life expands through cosmic night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night.
Hello everybody, welcome to this lunar stream tonight. Got a lot of special things for you. Before we go much further, I just want to welcome Daryl. Hello Daryl.
Hello, Mark. Hello, everybody.
Yeah, this will be neat. We actually are going to be using, in addition to the real moon right here, as you see, we're going to be showing it in conjunction with this tool here. This is the Lunar Reconnaissance Orbiter QuickMap. This is I have the moon in 3D right now. This is free. You can go and get it. It's at quickmap.lroc.asu.edu. What, Mark? What? Look up QuickMap in Google and it'll bring you right to it. And I'm going to show you the tools you can use as well. We're going to look at the real thing and then do a comparison here to show you how much you can deep dive. Now these photos are taken with the Lunar Reconnaissance Orbiter, so they are extremely good, extremely detailed, and go down to the smallest detail. Okay, but we'll get to that in a couple minutes. One of the things I wanted to show you was here in our real moon. We just check out the phase of the moon. We are now waxing gibbous, and we are not quite able to see the Aristarchus plateau yet, but it's coming soon. That's out here. We have Plato. This is Plato. This is a 60-mile diameter crater. This is Mare Imbrium. It's the Imbrium Basin. And what we talked about last time was how some craters ended up getting filled in by the same lava that overflowed in the Imbrium Basin. So when this meteor struck this older crater, it destroyed the wall of this crater and allowed the overflow of lava. Magma's when it's underground, lava's when it's exuded on the surface, to overflow and flood. Now, when you look at this, this is over 150 miles across here. So imagine just a 150 mile circle of lava just creeping in where you live. I mean, it's a massive amount. Okay, this of course is much bigger, the Imbrium Basin, and we have all these overlapping maria that we see here. Okay, we have these maria over here. All right, and if you want to know what those are, well, then what we do is we actually go to our LRO QuickMap. All right, and we'll zoom out. Here's the Imbrium Basin, Mare Imbrium. Okay, and if you click on it, you'll get some interesting data. Okay, so I clicked on it and it says Mare Imbrium, Sea of Showers. Okay, and it has a diameter of 1145 kilometers. The units are in kilometers. And so, and this is a beautiful Maria, the mare. Okay, sea. And it's a lava sea. It's not a sea of anything else, obviously. And then next to Mare Imbrium, we have Mare Serenitatis, the Sea of Serenity. If we go here and click that, okay, Sea of Serenity, okay, Mare Serenitatis, and it says Mare Serenitatis, and its diameter is 674 kilometers. Okay, we go to Plato, click on Plato up there, that crater, and we see it's named after the Greek philosopher, and we're also seeing that it is 100 kilometers, and that's about right because there's we look at 100 kilometers, and that is exactly 60 miles roughly. Well, it's just about. Yeah. So we're good. And then this is Sinus Iridum, and the Sinus Iridum here is a bay of rainbows. Sinus is a bay, okay, and Iridum is rainbows. Okay, Montes are mountains and so forth. So down below Plato here we have Montes Tenerife, we have Montes Rickley right here. This point here, right? Which, Sinus Iridum. Okay, see, now you're behind now. You're behind a little bit. So I think you mean the you're talking about Laplace Promontorium Laplace. Yes, that's that little deep here. Daryl's not able to see me real time, so his comments are going to probably be behind when we're talking about the QuickMap. So keep that in mind. Alright, so let's go back to the main view now, and we're in the main view, and so now we see these things that we're talking about. Now I can't rotate the moon like I could in the other, but this is the Promontorium of Laplace up here. This is Sinus Iridum. Okay, Plato, Mare Imbrium, Mare Serenitatis. So we're seeing these things. So every crater, if you're interested in looking at it and figuring out what these craters are, this is what you do. You view them here in real life, all right, reality, and then what we can do is we can go to the QuickMap and view them and see what they are. So we can bring this down, okay, and we can see that as we back out, all right, you'll see that we're here. We've got these two craters. We got this crater, that crater, and then we have Archimedes. And if we go back and look at our map, okay, we can see Archimedes and we can see these other craters over here. So now as the moon approaches full, we're losing contrast, okay? So the brightly lit areas here, there's no shadows really, so it kind of looks flat and barren. The only shadows we get are near the terminator, right? And that's actually a very interesting location to look at, right, when we're looking at the moon. So that said, we are here now looking down at Copernicus crater, and let's take some time to look at Copernicus here. Okay, and if we zoom in a little bit, right, and check out Copernicus, let me actually bring us over a little more.
Let me interrupt you for a
Yeah,
second.
please.
Carl says the music is overpowering your voice.
Okay, I think he might be right. I did that. Thank you very much. I had it turned up too loud, and my voice was a little too low. Okay.
You can always see what I say with Copernicus, Sarah. It always looks different from other craters to me. It looks like it was a great big huge mud splat.
It does. You're right. Yep. So here's Copernicus centered into view. We have moments of really good seeing where you can actually see this mud splat we're talking about. But if we go over...
Fantasy says it's still too loud.
I don't know why, but okay. Thanks, Fantasy. All right, there we go. So that said, now I think I will be able to come through just fine now. I also, when I was doing this, I wasn't looking directly at the microphone, so now I am. So that should help. Thank you, chat, as always. I do want to say hi to everybody who's here, and we have a few people here that we have seen before and some that we haven't. I'll say hi to Tim F., Carl Becker, Tiffany Echo. Hi, Tiffany. And Richard Minnick is with us. Hi, Richard. Thank you for the contribution. That is fantastic. And Dagger Spells is with us. So good to see Dagger and Fantasy. And we have Kathy Pernisek, who is KP. Well, I guess she changed her name for a moment. And that's what she said. And then, let's see, we have Daisy and Zoe Amethyst who have joined us, and Fantasy's with us. And no night would be complete without Kurt and the Goblin. Okay, it's good to see you both. And now I know that we have a lot going on tonight out in Benson. We got tons of things happening out there. And let's see. With that said, we're going to be doing a few more things in the QuickMap. Judy M is with us. Stuffy's with us. All right, and Carl Becker and Stephen Jarrett. Hello there, Stephen. Nice to see you. Thanks for coming back. And then let's see. I think that's it for now. Yeah, there we go. So anyway, if I missed you, it's not intentional. I promise. All right. So right there you can see Copernicus, and as Daryl says, it does look like a big splat. If we go into the Lunar Reconnaissance Orbiter map window, let's check it out there. And okay, when we get to Copernicus, you can see more clearly with the Lunar Reconnaissance Orbiter data how beautiful it looks. But I want to show you something else. Here's something we cannot do with SkyTour live stream. We can't come down here like this and keep zooming in and watch the detail get better and better and better as the better Lunar Reconnaissance Orbiter data is brought in. So we reach a certain point, and then we get the rest of the data, the good data coming in. All right. Now, if you look down here at the bottom, it tells you the scale. It's right now it's 19 and 20 meters per pixel, right? And we can even go down further, and as we get further in, and we get closer here in the hollows here in the little valleys, look at this. we're seeing individual rocks in the centers of these valleys. Look at these little shadows. Isn't this incredible? So this is one of the things that you can do with this product much better. And there's something else you can do, and that's in the map projection we're using, which is the 3D map. You can deproject and look at how it would look if you were on the edge of this mountain right here. So we're on the edge of a piece of the crater, and we can actually now look at what the rest of Copernicus would look like from here. Look at that. Now that is pretty darn cool. That's really cool. You literally get to see the actual data, and of course we could then fly right off of it and go up into the sky again, at least the moon sky. And so that's the cool thing. Now we could, for instance, let's go look at the center, this central uplift here, the central peak of the crater. Look at how ragged that is. That's pretty cool. Look at that. And we can also set down on top of it and say, hey, if we were to sit down on top of it, what would the crater look like from here? So let's go and sit right here. So let's say we came down here. Here's what Copernicus crater looks like around us. It doesn't look like you're in a crater. It looks like those are just mountains or something. But those are actually the symmetrical crater around us, along with the terraced edges. Okay, obviously we have other mountains in between here, so we'd have to back out. But this is a whole mountain in and of itself, and that's just the central peak, the bloop from the liquefaction that occurred when all the material was blown out and then came rushing back in like water, and then froze permanently in this little bloop here, just like a drop of water falling in a glass. And that's what's cool about this tool. You can do the most incredible things. Now, we can also, if we go straight up overhead again, we have another tool we can use. And again, we have in our main view, we have Copernicus crater here, right? And there's the central peak. And we get some fortunate seeing once in a while, and it looks pretty good. But if we were to come back in and look at our QuickMap, one of the things we can do right here is start using some of the tools. And here is the side where you're going to play. Now, we have different layers, okay? It's amazing what you can have. We can turn on and off the names, okay? So we turn off the names. That's nomenclature. Okay, I'll turn it on, right? And then what we can do is we can also look at all this other data. These are just overlays, all right? That is additional features overlaid on here so you can see. Now, if we close that, we have future mission sites, past mission sites, right? And here we can see all the different Apollo landing sites, and so forth. And we can just go to them. Let's go to Apollo 15, right? And we know where Apollo 15 is. I actually make a 3D model of that. So if we go over there, okay, now we're going to come over here and data will come in. And the Apollo 15 site is right here. Now we can actually select it, and you'll see all the detail. Okay, so if I show you this, it shows all the traverses, all the runs that they made with the rover. This is Hadley Rill here, and now it looks like it's lifted. It looks like it's sticking up, doesn't it? That's the illusion that happens on the moon. It looks like it's sticking up. Turn it upside down, however, and now look. Now it looks like it's a depression. It's the way your brain. It's the way your brain has the way your brain constructs shadows and three-dimensionality. Okay, but we can also do this. We can zoom right down in here. Okay, let's do that. Okay, and now we're down inside Hadley Rill, and I can just do this. And now you see what the astronauts saw. They went right to the edge of Hadley Rill, as you can see, right here. And that was the stations 8, 9A, or 9, 9A, and 10. And they overlooked and saw Hadley Rill. Now that's quite a ways down, but where it looks pretty steep, it's actually only like a 20-degree incline. They probably could have made it if they took a tumble, if they didn't get killed by it. But what's interesting is how this product has come a long way. These traverses were never in there before. You couldn't see them. And they're color-coded for the time they did them. And the rover is, I think if I recall, the rover is way out here. I have to look and see. It's labeled LRV, so wherever that is. Anyway, quite far. Look at that, huh? Yeah. Now, with the rover, they were able to go that far. I mean, if you think about it, that's pretty scary to be that far from your little oxygen bubble you've got, and you only have a temporary one on your back. So these guys were, they had nerves of steel. Okay. So if we come in here, what we can do is we can change the opacity right here. All right, and drop the opacity so that we can actually see. It's not doing it. Oh well. Not sure why, but that's okay. It should drop the opacity, but it's probably the labels. But if you come down here, one of the things you'll notice is we have the flag, right? And the shadow of the flag is actually visible here. Okay. And then we have the, well, there's the rover right there. That's where they left the rover. And then we have the descent module, the lunar module descent module. Let me turn this off for a minute. Okay, there's the descent module right there with its shadow. Okay. There's the rover out there. So they left it out there, then walked back, trudged back, and went back to the lunar module. Yes, of course. Yeah. That is correct. Yep. And in addition, the LRO is required to see the tracks left by the rover. And as you can see, not all the tracks are actually fully visible. You can kind of see them, and only the ones that have the highest contrast are going to show. Like we know they went all the way out here to Hadley Rill. That's quite a distance. So if we want to say, like, how far did they go, right? We can actually go right here. All right, bring this in again. All right, there's station 9. Here is the descent module. We can actually go here. This is this little tool here. And you'll see these little icons up here. This is to make a path. This is to make a circle. This is to make a measure. So we can say, let's click right here and then click over here. And how far was that? It was 1.95 kilometers that they actually went. All right. And we see that there. We can also inspect this and see how hilly the terrain was. And you'll see that right here. All right. Absolutely. Yes, it will. We can do that. So here you'll see that where the astronauts started, okay, They were climbing the entire time. Okay, if you look here, okay, that yellow dot you're seeing on the screen, okay, is following the profile of this line I've drawn. And right now, they started a little higher, then they went down low. Here, they were at minus 1,917 meters lower than the mean radius of the moon. That's the basis of all of it. And when they ended over here at station 10, okay, well, station 9A. And at station 9A, they ended up, or 9 actually now, they ended up another 1,000 meters higher than where they started. So when they looked back, they could see the lunar module on the plane before them, down below them. So it doesn't look that way here, but that's how this works. Now let's do this, as Daryl just pointed out, a really good thing to do. Let's now come back here and let's do the following. Let's measure with our tools. Let's say this side of Hadley Rill, and then come down through. Notice how it follows the contours and up to station 9. Okay, now we're going to see the contour. There it is. And right here, the depth of Hadley Rill at this point is minus 2,222 feet. And then when they come out just at the edge of Hadley Rill, it's minus 1,900 feet. All right. What? Yeah, I meant meters. Sorry. Yeah, it's always meters. It's 2,000. Let's see. 2,221 meters below the mean radius of the moon. Okay, the mean. Well, it's minus 2,221, and this is minus 1,899 or so, minus 1,900. So right here at station 9 is minus 1,900. So that's got to be approximately 300 meters below them. That's roughly 1,000 feet. So that's how big these features are. But now, when we zoom out of this, let's zoom all the way out and show you. Okay, you can see now with a good telescope we might be able to see like this, right? But obviously when we're looking here, we can't possibly see, as Daryl just pointed out, we can't possibly see the detail of what's going on down at this location. Even with a telescope that could show you this quality, we would not be able to see anything indicating lunar landing unless we got a glint off of the lunar descent module or the ALSEP experimental package or something like that. So hold on a minute. Oh, shoot. 1 second. Yes, you're right. Daryl is talking and he's not in here. Let me grab that. I'm going to put you in here. I did not. Okay. All right, now they can hear you. Sorry.
Whoa, testing.
There you go. They hear you.
Can you hear me okay now?
Yeah, they can. So, what you guys missed was Daryl asked how deep Hadley Rill is, and we were able to show it with this tool. The Lunar Reconnaissance Orbiter panel that I created here didn't have his audio in it, and I just did it, so we're good. So, yeah, they hear you now. Now, you also said something else about
that was a joke.
Oh, okay.
Go ahead.
Daryl also mentioned something, which I'll let him repeat, about the reason this illustrates the reason why we can't see any of the lunar landing sites from the Earth. So if you'd like to repeat that, because I don't think they heard that.
Okay. This illustrates why the question came up the other night, and it comes up fairly often. How big a telescope would we need here on Earth to see the landing sites? And there's no telescope on Earth that will reveal this. The LRO is only 30 to 60 miles high when it imaged these shots. So it's that close to be able to pick out what they can in these images. If you're on Earth, you're 250,000 miles away, and no telescope on Earth, or even the Hubble, I guess, would show the landing sites.
Yeah, that's true. And I actually did the analysis of the Hubble based on its sensor size and field size, and the entire Apollo 15 landing site, which is pretty much within here, never mind the Station 10 out here. This entire site here, about that much of it, that's 1 pixel on the Hubble telescope. So that means that a pixel is just 1 color. So we'd have a square that's 1 color. And we'd have to see all this additional detail in here. Only when we get way down here do you notice something interesting, you notice something amiss. And then you see the descent stage of the lunar module here. You see the lunar rover out there. Okay? And only as we get closer do those things become evident. And you can see the size of the pixels here. That's what each of these squares is, the pixel. And a picture is made up by many pixels. And this is how many pixels the Lunar Reconnaissance Orbiter has to devote to the descent stage of the lunar module. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 15, 16 different 16 or 20 pixels to actually flesh out and make that look like that area. Each of the pathways here, okay, we get down there, it's just basically 1 pixel of darker gray than surrounding, and that makes the path. So that is the resolution of the Lunar Reconnaissance Orbiter. And some of the Apollo sites you can actually see without any equivocation. You can see the shadow of the flag. And for those sites, the Lunar Reconnaissance Orbiter came down to 30 miles. And when it came down to 30 miles, it was able to pull out that resolution. So that's really cool. So that's the Apollo 15 landing site right there. And let me just turn it off. There it is. It's on. Now it's off. Okay. All right. And so if we back out, all right, that's way over there. And so, it's basically to the right of Archimedes. All right. And a little bit southeast of Autolycus. Okay. And Aristarchus. So that's where it is. And so when we look at our moon image, okay, we can move over here and see that we're talking about in here. This is where Apollo 15 landed, in here. In here somewhere, right? So that's interesting to look at that and say, wow. So we're seeing it live here, and then we see it in the Lunar Reconnaissance Orbiter QuickMap. All right. So we also looked at what it would be like to be on the mountain inside of Copernicus and see around from there. And there's a bunch of tools we can use to actually do some really good, pretty good science here. That is tied up in that actual QuickMap product. One thing I wanted to show also was, and I'll just get some of the craters in the view here. Another misconception about this moon is that the craters are all the same depth. Okay, so let's look at that, because when you look at this, you say, well, that Plato looks like it's this deep. Looks like it's the same depth here, same depth here, same depth there, same depth there. They're all the same depth. I hear that all the time, you know, and I realize that that's because people don't understand the moon like they may think they do. So let's just jump back to this, and I'll show you that. All right, so let's take a look, and let's go up to Plato. All right, and now we're going to do this. We're going to get rid of the past missions, and we're going to go into our data tab here, this little like GPS icon, and we're going to take this path guy. Right, I'll get rid of the old one. All right, take this path, and let's go down toward Plato. All right, and let's start out here and start and bring it up here, and then cross over Plato. All right. So now let's see what the bottom of Plato looks like. How far down is Plato? Okay, so if we inspect Plato, I don't want a polygon. Sorry about that. Let's do this. We're going to go here and go there. And the inspection shows that Plato's depth is, and the depth is right here. This is the depth number you want. The one at the bottom where it says terrain height meters. All right. That's the one that we're going to look at. And right now you'll see up there that it says minus 2512, right? And there's a tiny little uplift inside of Plato, but then it goes away. So 2520, 2512 minus. But interesting, look here. Look at the height here. I mean, this height looks like this height. You can't tell the difference. But notice this. Look at that. So here, you're minus 2512. You climb over the wall of Plato, and then when you get down to the Mare Imbrium, look at you. You're minus 3023. So Plato sits higher. Plato sits higher than the surrounding terrain. I mean, that's pretty fascinating, you know. So right there you see that Plato and the Mare Imbrium are at different heights altogether. If this was water and you broke a hole in the wall of Plato, it would rush out into here because it's much farther down, you know. So let's now go and say, now Plato was what, minus, let's say minus 2000. No, what was it? I forgot already. I'll get it. I'll just cross here and do this. So we'll get a depth here. And we're talking, yeah, it rises up. And so, like minus 2530 meters, 2,530 meters. Okay. And we can leave that there and come over here now. And let's go now. Let's go to Archimedes. And let's make another path and say, okay, here's Mare Imbrium. Let's go into Archimedes and cross through it out here. And now, oops, sorry, just a second. Okay, and now in Archimedes' case, look at this. Here's Mare Imbrium, and Mare Imbrium's minus 2474 at this point, but Archimedes now goes to minus 27, almost minus 28, and now it's minus 27, and the bottom is sloping upward. So craters are not all the same depth, and that's one of the biggest fallacies that I hear from people. You know, and like Aristarchus, let's do that. Cross through, and this is interesting because we're going to actually see. We're going to also include the apron of Aristarchus. We're going to cross right over the central peak.
Let me question you about something.
Yeah.
So Archimedes there was actually deeper than the surface of Mare Imbrium?
That's correct.
Plato was higher than Mare Imbrium?
That is correct.
Okay.
Right? Because, well, okay, let's put it this way. At this point, all right, at this point where Archimedes is, Mare Imbrium, all right, is lower than it is, or higher than it is here. Okay, Mare Imbrium was minus 3,000 and something meters here, right? And over here it's minus 2,000 and something here. Actually, it's minus 2474 right here. Okay, now some of that could be ejective from Archimedes. I mean, it could have gone a little further out.
What?
I mean, okay, see,
The mountains?
no, some of this height here could be the result of the impact from Archimedes.
I get it.
Yeah.
Sam asked, so how did they determine the mean lunar surface level?
Oh, the mean radius of the moon was a decided upon value that was effectively an arbitrary decision to give us something to measure off of. Okay, you have some plus areas, you have some minus areas. All right, the Aitken Basin on the far side of the moon near the South Pole, that's negative, was it 4,000 or 5,000 meters? And the highest spot is also on that side, and that's a plus, I forget what that number is. So it was an arbitrary starting point. Basically, they fit a shell inside the moon, a spherical shell, and said, okay, we're going to call that the radius of the moon. Now, it's hard because the moon isn't spherical. The moon is actually oblate. It's actually like a football's an exaggeration, but the moon is oblate like that. So, all right. Now Aristarchus over here. Let's just get Aristarchus again here. Right. You'll see the central peak now is in. You can see the central peak in Aristarchus here, and the yellow dot follows the line. So outside of Aristarchus, we're at minus 2323. Now we come into Aristarchus, and at the bottom of Aristarchus crater, we're at minus 4609. So Aristarchus is significantly deeper than Archimedes. Now it's minus 45, right? And then outside that, it's actually minus 2407, right? So the point being that when we look at this, okay, Archimedes here is only minus 2702, okay. The lowest spot in Archimedes is pretty much the center. That's 2764, just about. Then outside, it goes up. It starts going up. So this crater here, its floor is like 2,000 meters deeper than this one, or 1,000, 1,500 meters deeper than this one. So these tools show you how to handle the comments made by people when they say, "Oh, the craters are all the same depth," you know, and so forth. And the roundness of the craters is due to their impact energies. If something comes in at an angle and it's very, very high rate of speed, then it turns, when it hits that moon, it's going to basically vaporize. And when it vaporizes, all the energy is going downward. So it makes a circular crater no matter what the angle is, and depending on the energy. If it's a very slow-moving meteor, comes in at a very low angle, then it could drag out and make an elliptical crater. We've seen that. Okay, one such crater that has that is Goclenius crater, and let me see if I can just go to Goclenius for you. See if will this take me there? I might have to. I have nomenclature. I got to go in the nomenclature. Hold on. Go in here. And then I can filter from in here, I think. Let's try this. Don't know if this is going to do it. Oh, no, it's filtering on fields. I did it earlier. It allows us to just hunt for a particular crater. There we go. So let's go to Goclenius crater. All right, so we go there, and you click on it, and then this says zoom to right here. So if we click that, we're going to zoom to it. And here is Goclenius crater. Now, it looks like a crater. It looks like it's an elliptical crater, or a circular crater that's viewed from the side. However, it's odd because this is a circular crater, and we're at the same angle. So, why does it look like an ellipse? Because it's really an ellipse. See that? Goclenius is really an ellipse. Right? It really does look that way. Alright, so now when we, I had to go and do that, didn't I? Alright, so when we actually look at Goclenius crater, there's a few things that are associated with Goclenius crater that are really interesting. Among them, we have these lunar rills in here. These right here, these are collapsed lava tubes. And those are pretty interesting within Goclenius crater. Okay. But Goclenius is actually an elliptical crater. Why? Because the impact energy was one that was actually fairly low, and it was a very shallow angle of attack. Now, it was fast enough for this meteor to vaporize when it struck. However, it wasn't fast enough to make it a circular crater and spread that energy downward. Again, remember the analogy I gave you of the skipping stone on water. You throw a skipping stone, every time it hits the water, it makes a circular set of ripples. All right, but on that last splash or two it makes, it starts to slide on top, and it moves on and pulls it out in an ellipse, and then the rock will sink. Okay, at the end of that track. Well, that's what we're seeing here. It's kind of like a skipped stone that's running out of energy, but not enough to, leave the meteor behind. So that's what we're looking at there. So that's pretty cool. Now, craters like this one are simple craters, they're called. A simple crater, this is a simple crater, and as a simple crater, let me get rid of the filters so we can grab a name if it's going to show us the name. Yeah, Gutenberg, this is Gutenberg D. Okay, a simple crater has a bowl bottom. Now, why isn't it a bowl bottom? Well, because over time, this crater was probably a very early one. Not as early as this mare part here where this struck, but it came later, and what ended up happening was the bottom filled with lava from the interior and made a flat bottom effectively on this crater. And again, what's interesting is we can come right down in here and see in detail what's going on inside this crater. This is probably not the best example, but it's actually pretty good. And so if we go down the bottom of this crater and say, yeah, let's look around, what are we going to see? Well, this is what we'll see. These are the walls of the crater as seen from inside the crater. And right now we're probably like several hundred feet above it. What's that?
And you can see the more you go down, the more craters there are. Craters after craters after craters, smaller and smaller.
That's right. The moon has been pelted for billions of years. And without erosion, well, then a crater like this one is filled with these tiny craters along the bottom, as you can see, as Daryl just pointed out. And it doesn't take much altitude to lose those craters and see that they're not there anymore. You don't see them. These are not craters we can see with telescopes on Earth. You need a lunar reconnaissance orbiter to do that. Now, one of the things that happens too on the moon is some of these craters, they have walls that are like 20, 22 degrees. Seems to be the average of crater walls is around 20 to 27 degrees. And you'll notice sometimes that there are streaks down the side of the crater, and these streaks are places where a boulder at the top got loose and started rolling. Now, that's not what these are. These are stitching artifacts from putting all the photos from the Lunar Reconnaissance Orbiter together. But there are some simple craters that show this very issue, and it's really quite impressive. So we'll try to find those, because I'd like to show you those if we can. Meanwhile, back on our main view, all right, our moon is still happily hanging out for us, and I think that we're actually able to see that here we've got some ray structure here. If you want to know what this ray structure is, we go to the Lunar Reconnaissance Orbiter, a QuickMap, and we look for it and we figure it out. Now, one of the other things is if we bring ourselves down here, okay, this is now toward the south pole of the moon. All right, you'll notice where the telescope's pointing, it's pointing almost straight up. All right, now we see, in fact, that on the south pole here, we have, we're not at the south pole yet, let me get there. There's Tycho. Okay. Remember Clavius yesterday? Well, Clavius is now here, and Clavius is pretty washed out now. It's not quite as contrasty as it was last night. Remember, the shadow was a little more here. Well, as the moon continues going around the Earth, more of it appears lit up from our point of view. And so that's why we have the moon phases happening the exact way they do. So we have these here. We have Clavius here. I actually have Clavius still here on my desk. And we can't see it yet, but Aristarchus is also available. And I printed Aristarchus crater today. Took about 30 minutes to print that. And I went and I painted the Aristarchus plateau with the white you see next to Herodotus. And Schroeder's Valley. You can see the head of the snake here going back. Let's see, it's right. Yeah, it's right here, heading back. I know it's hard to see, but in any case, this is 1-to-1. This is actually not exaggerated altitude, and so this is kind of what it would look like in real life. So
I have a question.
Yeah.
To the left of Tycho,
Yeah.
in your live image, to the left, there is a very elongated object near the terminator, right there.
Yeah.
Can you identify that? And is that an elliptical crater?
It could be. Let's go find out. So let's come back here, and let's go out. Now remember, we're looking at a 3D model of the moon here. We can change our model. Okay, let's go to orthographic near side, and that will show us the moon as it is. And I'm going to turn off, well, I can leave it on. I can just go down here and it'll start pulling away. Let's go to, well, let me, yeah, I should have. I will turn off the names for now. All right, and all right, let's go to Tycho right here. And right to the left of Tycho, I know what you're talking about, there's an elongated crater on the terminator. And it's going to look different here. There, I think that's it.
You're not showing LRO right now.
Oh, duh. Thank you.
I'm having a hard time keeping up with you. Okay, so
this might be the elongated object, or maybe that's this.
No, down, straight down, right there.
This thing.
Yes.
Yeah, that's what I was just circling. Oh, I see. You're behind. Sorry. Okay. Yeah, that might be it. So now we can actually turn on the names and go see what that is. Looks like Schiller. Schiller. Schiller crater. And that is very interesting. Now what I want to do is now see if you get in there and you say, wow, well, what is that? Okay, let's say it's Schiller crater. We can now go into the 3D globe of the moon, and what it'll do is it's going to show us the 3D object that we're looking at. All right, and here is Schiller again. All right, and so we can zoom in on it and see just what it looks like. All right, so the data is coming live over the internet, by the way, so we are... All right, so now there's Schiller, and that's what we're talking about. That's what we identified from the image earlier, which was over here.
Certainly looks elliptical.
Right there.
Looks almost like a number of craters strung together, maybe to make the ellipse.
Yeah, and
Maybe.
and we can go back and look at it, and I will say that that's what this looks like. But keep in mind, look at this. It has this central peak, which I know you can't see in real time here, Daryl. Schiller T, it's called. It has a central peak that seems elongated. So I'm wondering if this is some type of hybrid type crater of some kind. You know, because here we look at this, and we come down inside Schiller. See, guys, this is why I don't get any sleep. Because I'm doing stuff like this. Alright, so here, you can see this long chain of mountains. Again, these are from the impact. And so something hit here, got vaporized, and left behind, probably punched a hole in the moon enough to allow lava to well out on the surface and fill the area. So that's what's something interesting to understand. When you look at a central peak system like this, you have to understand that the flat bottom is a filled in area with lava after the impact. The original crater, the transient original crater, was deeper and was probably much deeper in here, going underneath and down. So the bottom of the actual crater is deep inside here, underneath all this. And most of the craters are like that. Most of them are going to have these gigantic excavations with a large central peak, and then they fill with lava. And so the central peak, if it's big enough, will stick out a little bit, like with Copernicus, and so forth, like with Tsiolkovsky. So there's a number of things that go on the moon that are literally endemic to the moon alone, because of its 1/6 gravity. And, yeah.
Oh, okay. It's kind of what I thought. Schiller is thought to be a fusion of two or more craters.
Mm-hmm. It could have been impacts that occurred near the same time. All right, but you see this central peak system here? We've got one here, we got one here, and then this one here may have had a central peak at one point, but it may have gotten maybe underneath the lava here, for all we know. But yeah, I mean, it kind of looks like three. And if we actually go up top, let's go to this. If you draw the profile around this, you can see a logical, at the bottom here, this is a logical separate area. This is a logical separate area. And this is a logical separate area, as is this. So there might have been maybe four potential meteors that struck one after the other, again torn apart by the moon's gravity as they came in. This is all cool stuff. It's all the stuff that's really, really neat to think about. What's interesting is, we say, oh, well, it's to the left of Tycho there, in our view. But Tycho's nowhere to be seen here. Tycho is over the horizon here, So this crater has no knowledge of Tycho. If there was anything there, it would be quite a hike to get to Tycho, actually. Probably a long trip. So if we back out of here, okay, we come over here. Here's Tycho. However, the ray structure from Tycho reaches Schiller. So that's interesting. Now, if you see a ray crossing inside Schiller, well, guess what? Then you know that Schiller came before Tycho.
Yep.
And as we notice right here, there is a ray structure here. All right? There's a ray structure. So it looks like Schiller was here before Tycho. You can see the ray. And so that's, again, part of the chronology, the history making of the moon, right? Where you can create the history of the moon by looking at the craters and figuring out and remembering, think 3D, there's stuff underneath the surface and stuff at the surface. You know? The rays, when they're made, that material happens within the first few days of the meteor strike, because that stuff gets thrown up in the air, and then several hours later the early stuff starts falling, and then maybe it takes another day or two for the rest to fall out of the higher areas of the area around the moon and in the land. But it's going in one direction. There's nothing to make it go away. The gravity of the moon is pulling it down. So maybe large cratering ray structures could take maybe a day or a day and a half or so to actually be made, because that's about how long it would take for the stuff to go into the exosphere. That's the non-atmosphere area around the moon, because it has no atmosphere, and then fall back to the moon. And it's only 1/6 gravity, so it'll take some time. Big stuff falls down quicker. But I would love to see a meteor the size of Tycho.
Galileo might want to argue with you about that,
Why?
saying that the bigger stuff falls faster in a vacuum.
Oh no! That's not what I meant.
That's
I meant-
what it sounded like.
No. The bigger stuff. Okay, it's gonna not go as far, so it'll come back to the moon sooner, because it's not making a high arc over the moon. It's gonna make a smaller trajectory from the impact site. Okay.
All right.
That's what I was talking about. So not because there's a famous Apollo experiment. A guy had a feather and a hammer, right? The astronaut, and he dropped both at the same time, and they both fell to the moon at the same time.
I was about to mention it.
Yeah, I mean, I love that experiment. I actually taught that for years in classes to show people, and I showed them that video. And I asked them, what's going to hit first, the hammer or the feather? The hammer, the hammer. It's like, yeah, well, it's only air that causes that to slow down the feather.
We have talked about Schiller before. I remember this, an elongated sort of crater over toward the southwest limb of the moon.
Yeah.
So we have been here before.
Yeah.
Neat looking, whatever it is.
Yeah. And I agree. It's probably does have a fundamental origin with 2 or more impacts. But there it is. Yeah, there's another one here. Notice it's like a little potato shape here. See that one? You see that one, right?
I see it.
Yeah, okay. Well, I asked, you didn't answer. And so the question is, what's that one too? We can go back now and figure out where that one, what that one is. So that's going to be up from here. And is it this one? Is it Hansel? Looks like, yeah, this is Hansel. Or Heinzel. Let's take a look.
That one does look like overlapping craters.
Yeah. Yeah, this is Heinzel. Yeah, and you'll notice you have all these other craters like Heinzel L, Heinzel R, Heinzel T, Heinzel S. Those are known as satellite craters. Now, one of the things is that you look at these craters, some of them could have been made at the same time as Heinzel. Okay? But some of them may not be associated with Heinzel. And they could just be because they're near Heinzel. They don't necessarily have to have happened when Heinzel happened. That's one of the things about these satellite craters. But Heinzel's pretty too. Actually, you can see it's got that look. See, this is a good look too. You can actually see the elongation, right?
Isabella's here.
Hi, Izabela.
Happy birthday.
Yeah, that's it. It's her birthday. I sent Izabela a SkyTour hat, and I took the dirt from the new observatory and I wrote STLS in dirt on the brim of the hat. She asked me to do it, so I did it. And I guess she's gonna check tomorrow. I was trying to get it there for her birthday, and it didn't get there in time apparently.
I think she's expecting it on the 12th.
Yeah, she's gonna check the post office tomorrow, I thought she said. We'll see. Yeah, so that's Heinzel. That's what we're looking at there. And if we come back into our main view, there's Heinzel now. In real time. See that?
What it is.
What it is. Yeah, very nice. And so there's a lot of features that you can look at on the moon, whether in binoculars or the telescope, and then go into the QuickMap and figure out what you're seeing. It's very, very cool. Very cool indeed.
Let's go back up to Copernicus for a minute.
Okay.
I always say that about
Yeah, refocus
about
here.
Copernicus looking like a big mud splat.
Yep.
And I realized that all that's dry as a bone, and it was when it happened. It just sort of has a different characteristic look to it than other craters.
Yeah.
The way the ejecta came out. I wonder what would cause that. Just what the impactor was made of? Wet or not?
Well, no, I don't think there was any water involved at all. I think that what we're looking at there, okay, if we back out a bit, okay, you can see this splat. Copernicus was more of a direct impact, straight on. You know, some of the craters that aren't straight on, some of them don't leave any rays at all. But Copernicus, it was a very high energy impact, and it sent out a lot of material. And the reason you know it's high energy also is if we come back to our LRO QuickMap here, and let's just zoom out for a bit, and let's go back to Copernicus in here. All right, let's get there. Oops, I'm going the wrong way. Easy to do on the moon. Don't get lost in the moon. Okay. Okay, that's the pole. I want to get away from the pole. Yeehaw. Okay. Alright. Let's do this. Alright. And get ourselves back here. Right here. Okay. So here with Copernicus, if we zoom in, let me spin us around to actually make it more like it's supposed to be. More like we're used to. Okay. Check out the way Copernicus looks inside. It has a central peak, yes, but then it has these rings of terraced material. And then this stuff here was literally snow plowed out of the center by the impact. And the ray structure, I mean, that's pretty even on all sides, which implies that the impact was straight down for this impactor. And the ray structure is actually in this direction now. Apollo 12 and Apollo 14 were somewhere around here, and they landed in the rays of Copernicus, just to sample material that was dredged out of the interior of the moon.
But even then, you look at the rays and they look different than, say, on Tycho or in the other major craters.
Yeah.
They look like a big splat.
It does. It does. This area here, this apron, is just a massive, blob. Tycho hit in the highlands. Okay, so we don't really get to see a splat. This here struck on a mare. Okay, and when it strikes in a mare, that makes a different set of patterns than when you strike in the highlands.
Oh, that's a good point. I understand.
Because the mountains will deflect and obstruct and actually direct rays to go in specific directions because the mountains obstruct them. But Copernicus is clear. And I do notice a lot of the stuff up here that could be from Copernicus. Really interesting. And it also has an extremely complex structure in here too. So I wonder if the object that hit Copernicus location might also have been spinning rather rapidly when it struck. It might have been spinning rapidly, which could account for why it went out in all directions as it did. And then was had these very, very fancy and complex tentacles and tendrils within it. It's something else. It's really, Copernicus is quite an amazing crater. I'm noticing that our focus is off here. Look at that. Let me see if it might be temperature related. Let me just dig that down again, see if that helps. Oh yeah. Yeah, that's helping. So yeah, you can see the rays here. Really fancy ray structure, very complex. I'll say one thing though. There's another crater that I think is actually just as interesting, and it's the one right near it. Okay, this one. This is the one that we're seeing over there. This crater here. Okay, let's zoom in. Kepler. Okay, look at the complexity of its ray structure too. Again, it hit on the mare, and so it can send stuff out in all directions, and of course it's going to be lighter material going out on the darker material, which is the mare. So it's going to show very brightly, and so Kepler shows this too. So in our view, if we go back to our main view, okay, there's Kepler right there.
Oreos and mascarpone and chocolate. Isabella's cake.
Oreos, and I don't even know what that is.
Mascarpone. It's an Italian.
Oh my gosh!
It's like a cheese.
I didn't know that.
It's like a soft cheese.
Well, Izabela, since I sent you the hat, you'll have to send me a piece of your cake. Can you imagine that? Shows up, it stinks to high heaven, you know, decaying in the box. Well, very cool. Very cool, Izabela.
So, in your live view right now,
Yeah,
the little crater to the upper left of Copernicus,
that one.
that one, is that what you were talking about?
Yeah, I think that's Kepler.
Oh.
Because it has that really big apron around it. You know? So, I believe, let me just, yeah, that makes sense. So, yeah, so, Kepler was the name of one of my greyhounds when I had a greyhound dog, and the other one was Tycho. So Tycho and Kepler were my two dogs, and you know, they lived very long lives, 13 and 14 years old apiece, which is long for a greyhound. And so they were good dogs, needle nose. Like they look like a pair of needle nose pliers coming at you.
And the real Kepler worked for the real Tycho.
That's right. They were contemporaries, and that's why I named the dogs Tycho and Kepler, because they initially didn't get along, and Kepler and Tycho were at times at odds with each other in real life, you know, as contemporaries.
Yeah.
So I named the dogs that because it made sense. And Kepler was always getting in trouble with Tycho, always trying to instigate. Very nice, yeah. So,
Well, Kepler's the guy who wrote the 3 laws of planetary motion.
he sure did. He sure did. Based on observation, too, which I thought was pretty interesting. Wow, okay. Don't forget, guys, while we're looking at the moon, just look for anything that might be crossing it. And it'll be going from this way, from right to left usually, in this direction, kind of on a diagonal.
There is a crater to the upper left of Copernicus, right on the very terminator, right there.
Yeah,
Can you zoom in on that?
sure. Let's also see if we can identify it. There's mountains right behind it, and it's at the extreme left edge of Mare Imbrium here.
That's too big to be Aristarchus, isn't it? Actually, I would have to wait again.
Not necessarily though, Daryl.
There too.
But it doesn't have the white expected glow of Aristarchus, but that could be Aristarchus.
Well, I mean, it's right on the terminator.
Yeah, that could be Aristarchus, but
I don't know. There's another crater right next to Aristarchus called Herodotus,
yeah, that could be this.
and then Schroeder's Valley.
Yeah, that's up there. If that's it. Yeah, let me look at my model here. Actually, okay. If this was Aristarchus, we expect to see some mountains here, and they're there.
Yeah.
And then beyond that would be Herodotus, but you might not see Herodotus because it's a very low-walled crater. But the mountains would block it from this perspective.
Well, we'll know in a day or two.
Yeah. Well, it should be simple to figure out because we got this 1, 2, 3 craters, and they should point right at it. Right? So I would expect that we would be able to figure that out.
Maybe with the QuickMap.
Yeah. Alright, well, let's go check out the LRO. And let's get rid of this. And we'll get rid of this. We'll go to full screen here as best we can. Alright, so this is approximately the angle at which we're seeing the moon right now on our view. Let me just confirm that. Yeah, it's about right. So the angle is more like this. That's about what we're looking at. So
that is Aristarchus there.
right there. So I'm wondering if, get out of there. So from here, we go to Plato, to Copernicus, to Aristarchus, almost makes a 90-degree apparent run. So maybe that's the only crater over there that could explain it. You know? And that could be the Aristarchus plateau we're looking at. I'm also noticing, if we zoom in again, I'm also noticing that it has some brightness on this side too that might be that. And we've got some pieces here. Oops, sorry about that. Over here that might lead to being able to figure this out. If it's Aristarchus, we should see these as well. So over on the LRO QuickMap, because we just see this as on the Terminator.
On the LRO, just to the right of that's I can't quite read it. To the right of Aristarchus,
Yeah,
there's a faint half crater
Prince,
and some rocks higher up.
Monty's Harbinger. Those are you talking about?
Yes.
Okay.
I mean, is that what we're looking at? What you noted off to the right of Aristarchus in your live view?
Except that we're looking at illuminated far side of a crater. It looked like, right? Let's go back. Yeah, we're looking at the far side of the crater being illuminated, and this is the near side. There's the far side. And the near
Well,
side.
in your live view, I mean, those little features there to the right look disturbingly like what you had in the LRO QuickMap view.
Let's go back and look. All right. You mean
Those
these guys?
objects? Yes.
Yeah, those three look like those could be it. Yeah. Yeah, we're not seeing Prince at this point because of the lighting or whatever. Yeah, so that's probably Aristarchus, and we're looking at this wall of the crater that's reflecting the sunlight. It is very bright. It's the brightest feature on the moon. You know? And
Yes.
actually, I'm making it really hard for us. I can just say, I can just do this. And like that. And so we got 1, 2, 3, and it points at that. So that's Aristarchus. And that's bright. And then around the corner, Oceanus Procellarum. Sea of Storms. Yeah. Very nice. And so, in our view here, we don't see Prinz crater, which is right here, but let's try actually increasing the light a little bit And now we do see the wall of Prinz right here. Look at that. So we do see it. Very nice.
And we can't quite see Schroeder Valley yet.
No, it's just on the darkness right here.
Yeah.
I'm not able to see it.
All right. So we did find Aristarchus.
Yeah, it's just starting to come out. And, yeah, Prinz Crater is actually right there. You can see it. Right near Aristarchus.
Yes.
Yeah.
It's like about half a crater. Just the wall on the right's really visible.
Yeah, yeah. And you can kind of sort of see that. Very nice. So that's very interesting to do that. And the thing is, if we let's look at Aristarchus for a minute. Again, over to the LRO QuickMap.
You see the light on the mountains immediately west of Aristarchus. The light has changed just in the time we've been here.
Yeah, over here. I noticed that these mountains are illuminated more than they were just a few moments, earlier tonight. Now I also did increase the exposure, but this is about what it was. But this little peak right here, I don't remember that being there. You know, but it has changed quite a bit.
Yeah.
Well, let's go back to the LRO QuickMap for a minute, because I want to show you something else. All right, so we go back here, and now I'm going to go back to the projection, which is going to show us the lunar globe, and it'll come in here with Aristarchus again. All right. Alright, so we come down to Aristarchus now. And this is what Aristarchus looks like. Here is Schroeder's Valley. This is Valles Schroeteri. Again, a lava feature. A lava tube underneath. Collapsed. This is a real... It's also possible that it was created from moonquakes that occurred at some point in the past, but usually they're lava features like these things here, those things here, those things. Go ahead, you were going to say something?
It looks like a, I can't say it in mixed company.
Yes. And we're very mixed.
Herodotus is a cool crater all by itself, too.
It is, look at that. Yeah. Now, those mountains we saw illuminated, okay, let's go down low here and see. Well, there you go. Here is the mountain that we saw illuminated in our other view, and if we come back to it real quick, I show you. Okay, there is the mountains that are illuminated right there. Right here, see those? Those are illuminated, and we're seeing those in the quick map here, especially when we get down low like this. So the sun is hitting these and we're seeing them. All right. Now, if we come over here and let's do a little measurement. We can come take our measurements. I'm going to do 2 measurements. I'll show you why. If I start from this left wall and I cross over the crater through the central peak and stop at the other side, okay, like right here, all right, we get 1 set of values. All right, now those sets of values represent the actual path down into the crater and up again. So the total distance that it's going to be here is going to be more than the actual diameter of the crater. So to do that, we basically will come back here like this, and we'll say, let's go from like here to about here. Okay, right about there. Or right there. Okay. Now, Aristarchus has a diameter of, what was it, 36? I think it's 36 kilometers.
I don't recall.
But this is a straight line view, and okay, this is a view. This line, anything other than a straight line, is going to be a little longer if you stretched it out. So this line will be a little longer than this line here, and that's kind of what we're looking at there. That says 38.528. Okay, let's see what this path was. 38.7. It says it's less. Well, I didn't get to the far left side, obviously, and I missed the left side here, so it's actually a little longer. That's okay.
And why is Aristarchus the brightest object on the face of the moon?
Well, that's an interesting conundrum, because it could be that it's the youngest feature relative to the others,
Yes.
and that would make it the lightest because the radiation hasn't darkened it, which radiation tends to do.
It is a young object. Relatively young.
Yeah, and so radiation will eventually darken Aristarchus. Now, you might have remembered Oumuamua when it came through. Oumuamua was originally thought to be this long, thin object. It actually wasn't. It was actually a big pancake. It was a flat, large, discoidal-shaped object, which is why people said maybe it was a defunct solar sail, because it was a very, 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 very large, flat object, but not very thick. So that seemed like it could have been like a solar sail. We never got a picture of it, so we don't really know. However, I will say this: Oumuamua, when they looked at the color of Oumuamua, it was almost a deep crimson red.
Yeah.
And that crimson red is the result of ultraviolet radiation and cosmic rays hitting something for billions of years. It actually causes light stuff to turn dark, which I thought was interesting. Now, another little aside that we haven't talked about is, what does the moon smell like? Remember that?
Gunpowder.
That's one of the things they thought of. Another one was burnt steak. Was another suggested smell. Now, only the astronauts in the lunar module could tell, because when they came into the lunar module, they still had dust in there from the lunar dust. So they thought maybe that it kind of smelled like gunpowder. Now, what's interesting about those smells, is that those smells are the result of being bathed in radiation. Okay, those radiative odors from the particles are the result of billions of years of radiation striking them. And so it's possible that is the smell of space. Gunpowder or burnt steak. Pretty interesting. So now let's look at Aristarchus here. Let's go through it, and you'll see a little yellow dot. See the yellow dot in the middle of the crater? It's moving around as I move this. That tells you where in Aristarchus we are. So at the tip of the central peak right there, we're at minus 2975 meters, 2,975 meters minus, below the mean radius of the moon. Okay, and then the base of Aristarchus in here is minus 3,174. Aristarchus is pretty much the same. Okay, it's actually fairly the same throughout its bottom. Some craters are sloped, some craters have different terrain levels. Aristarchus is actually really flat in the middle here. And then you go up the sides, and the average slope of the sides you can see given in the blue over there. right here. Okay, that number. The average slope of the sides here is 10 degrees, and it goes as much as 23 right there. Okay, 25. So these are terraces now. Again, terraces. You know, pretty interesting.
Mark, excuse me a moment, please.
Sure.
Be right back.
Okay, so are you guys enjoying this this combinatorial stream where we're actually looking at the real moon at these features and then looking at them again with the QuickMap? I'm going to see if I can. I kind of did go a little over on the exposure. So let me know if you guys like this. Hey, Dean Bustador, how are you? Yeah, let's let me try this. That looked okay. Yeah, so again, we're hanging out in Mare Imbrium here. And as you can see, the moon's very bright, so we have to literally shut down the exposure if we come off the terminator. Bringing it up can show us some stuff. I mean, this is Aristarchus crater, this is Copernicus, this is Kepler, this is Sinus Iridum, Mare Imbrium. Okay, then over here we have Archimedes, we have Plato. Plato is 60 miles in diameter, right? And so the Apollo 15 landed here, inside here. The Hadley Rill is in here. Okay, we can't really see it. It's actually a very small feature seen from the Earth. So there's a lot of cool things we're going through on the moon right now. And the other thing that's interesting that I love to talk about is the order of events on the moon. We've talked about that. But see, these Maria here, large impacts, this very big circular impact, that's now the object that hit there wasn't that size. The object that hit was probably, maybe 70 miles, maybe the size of Plato, maybe a little bit larger, but it struck with a lot of force, struck with a lot of speed, and so it managed to puncture into the moon while the moon was still young. It still had a lot of molten material inside of it, and they overflooded this entire region. It might have taken some weeks for that to actually happen, you know. Let's do this now. Yeah. Izabela says, wow, you can build a big city in this crater. Exactly right. Hey, Dixie Belle, how are you? Nice to see you. Hi, and Sherry, how are you? Nice to see you. Yeah, so I think that one place that now when the moon gets full, guys, we're not gonna stream because the brightness of the moon will completely overwhelm trying to look at other beautiful objects in the night sky, and the brightness of the moon will also make it so that most of the features are going to look like this. There's going to be no shadows, and we're not going to be able to see too much. All right, we're going to get light bouncing right back to our eyes, like in some of these craters already, and that's going to be removing most of the contrast. So we're not going to get contrast except at the very extreme edges. See, here you can actually see that.
Did you know that's called the opposition effect? The moon being at opposition when it is truly full, 180 degrees from the sun in the sky. If you see a half-lit moon, like at first quarter or third quarter, you would think it might be half as bright as a full moon. Actually, the full moon is 9 times as bright as a first quarter moon. And the difference is because you are literally seeing no shadows. The shadows are directly under every rock you're looking at on the moon, so you don't see them.
Hmm.
And it's called the opposition effect.
Make sure you memorize this, guys. There's a test. That's actually a pretty cool effect. I think that I think it's kind of important to make people aware of that, Daryl. So nice job. That's a good thing to know.
It's the way things work.
Mm-hmm.
That's why, I mean, when you look at a full moon, the light is very flat because you're literally seeing no shadows.
Yep. Kathy says she attended a lecture by Avi Loeb on Oumuamua after he made the observation of the object. It was at Penn State in Erie, Pennsylvania. Very lucky to be there. It was very interesting. That's cool. And he didn't tell you what he really thought because, and you guys know I worked with Avi in a couple of shows, but he didn't tell you what it was. He didn't tell you what he thought it was because he was trying to. How do I say this? He didn't want to rush headlong into the UFO community because he knew that would become the all-consuming thing that becomes his nemesis over time, you know. But I'm in the UFO community, and now he's in there, and he's gonna probably stay there, you know. He's probably gonna stay there.
Carrier. And that always kind of struck my fancy.
Yeah. But it turned out that it was more of a pancake.
Pancakes aren't as much fun as aircraft
I know.
carriers.
Remember Ultima Thule when the New Horizons probe went past Pluto?
Yeah.
It ended up going out to Ultima Thule, and Ultima Thule was something called a contact binary. And it was two pancakes that managed to be orbiting. They were orbiting each other, and then they contacted each other. Now, out in deep space, when two things strike each other, there's a tiny bit of heat generated by that impact, right? Because the energy of motion, called kinetic energy, is turned into thermal energy on impact. So the ice between them, and they're coated liberally with ice, melted momentarily and then refroze almost immediately. So now they're welded together unless something else comes along and hits them. And so the Ultima Thule looked like this double pancake just rotating slowly through space.
It's called Aristarchus now, is it not?
Oh yeah, they had a name for it. I don't remember the name.
Aristarchus. Arrokoth.
Oh, Aristarchus, that's right. Yeah, I remember that.
Anyway,
Yeah.
I still like the idea of alien USS Nimitz flying through space.
An alien Nimitz. That's good. I like that too. I like that too.
That's sort of like Battlestar Galactica, you know?
That's right.
Very much like.
Yeah. In fact, that would actually be a very good science fiction premise for a show.
I think it already has been.
What, that Ultima Thule was an alien?
No, I was talking about Oumuamua being an aircraft carrier.
Oh, that was done in science fiction already?
Battlestar Galactica.
Oh, I see what you mean. And Battlestar Galactica came way before Oumuamua. Yeah.
Well, it depends on which one you're talking about.
That's true.
One was in the 70s. The other one was, it was shortly after 2000 or 9/11, 2001.
Mm-hmm.
So what's that crater right there? It
Yeah, I'm going to identify.
looks like an apple.
Yeah, this looks like an apple with a little leaf on top, and it's sitting. Well, it could be a snowman, right? A very oddly shaped snowman. Let's go check out what that might be. Okay, so let's back out of here.
Dean says Gassendi.
It might be Gassendi. I was wondering because I have to go look at it from this perspective. All right, so it's going to be is it down here? I got to get the angle right. Wait, let's do this here. Oh yeah, the angle is not correct. Have to get the angle right. Alright, so getting the angle right from Copernicus. It's down here.
I think Gassendi is right down to the lower left.
It's here, yeah.
It's to the left now.
It's right here. Actually, oh, you can't see it, but yeah. I gotta.
There it is.
Yeah.
That's Gassendi right there.
Yeah, and it sits above. And thank you. That was Dean who said that?
Yes.
Yeah, he was right.
Way to go, Dean.
Very nicely done. And we are also in Mare Humorum, which is the area within which we are. Mare Humorum. And let's see now.
That's the sea of comedy, folks.
Hey, that's funny.
What is humorum?
Sea of Humors.
Would that be vapors in the old idea?
Yeah, Sea of Vapors, I think it was. I'm trying to find the name here. I thought they had it.
Didn't have it right in the middle.
Oh, maybe it was.
I think it says it right there.
No, where is it now? Oh, feature info. Let's try that. Yeah. Sea of Moisture. It's a sea of moisture. There's no moisture on the moon, guys, but you know. All right, but I was on the wrong tab. But yeah, nicely done. That's Gassendi. This is the Mare Humorum, Sea of Moisture. You gotta wonder what they were thinking. But then again, you know, sometimes moon features were named before they really knew a whole lot about the moon. I don't know when that happened. Actually, we can find out. Because,
Well, Galileo called them seas, didn't he? I mean, he knew they weren't water, but
well, he didn't know what they were, though. Yeah.
Tixty Bell, every single thing you can see on the moon has a name.
Well, there might be some craters that are available, though.
Small enough.
Yeah.
Every major thing you see on the face of the moon, at least on the near side, has a name. I was curious, do you still have Gassendi up in
Hello? Yeah. Let me go there now.
You can see that line of peaks or something in the bottom.
Where? Down here? At the bottom of Mare Humorum?
No, the bottom of Gassendi.
Oh, the bottom of Gassendi. Maybe, you mean the walls of the crater?
No, in your live view, it looked almost like a light line across the running up and down in the lower part of the crater.
Okay, let's go see that then. Oh, I see what you're talking about.
Yeah, well, yeah, there's the central peak. It does look like the line sort of continues down toward the south.
Yeah. You're talking about this feature.
Yes. Yes.
Okay, well, let's go see what that feature is. All right. Oh, I see. So there's another crater here, Gassendi N, and it looks like there's some lighter material here.
Oh, a lot of rills in the bottom, too.
Oh, yeah.
Okay, it was probably the light in the smaller Gassendi craters.
Maybe.
Uh,
But there is a haze here. Look at.
yeah.
It looks like there's a. Maybe that's an overlying ray from another crater. I mean, we got this out here too.
I thought the rills looked really cool.
Yeah, they do. They do. And that's neat stuff.
Ooh, zoom in on it.
Let's go in here and see what we got for. Oh, I have to. I'm going to my lunar globe actually. For this one. Alright, and now we can come down and just check it out from inside Gassendi. Wow. And there's Mare Humorum out there. Wow. This is neat. I like this. I like being able to crater dive within LRO. That's really kind of cool. Let's see if we can see Gassendi B. Let's go over to our startup here, our stream. Oh yeah. There's Gassendi B. This is Gassendi, Gassendi A, Gassendi B.
Yeah.
Yep.
If this telescope was working at f10, we could see down inside the crater better. Probably see Gassendi M and N.
Yeah.
Gassendi.
Well, if we get some sympathetic seeing. I mean, I can start to see right in there. You can see one. And there's something there. I don't know. That's cool.
I think that's the shadow of the central peak.
Might be.
Anyway,
That's cool.
congratulations, Dean. You nailed it.
Oh, well done. Dean Bustador also wants to know about transient lunar phenomena. Well, let's go back to this. Okay. Let me kind of bring that down a little bit. Okay, because... oops, wrong way, Feldman. I can't wait for the rotator. Okay. Because this crater, Aristarchus, which is this crater here that I have, I printed it out today in 3D on our SLA printer. This crater is actually a source of many transient lunar phenomena.
Yes. I mentioned before.
Yes, you did. Many times. Yeah.
This is about the hottest hotspot on the moon for transient lunar phenomena.
Yeah. And the reason is not clear. We don't know why. It is a true mystery. We don't know why it's such a hot spot. you know. But hey, it's not bad. It looks pretty cool. And I want to also update you guys while you're here. I've made some inquiries and applied for some grants, and don't know if we'll get them. But if we do, we're going to add yet another telescope to this building, and it's going to have a full-blown spectrograph on it. And the spectrograph will allow us to take spectra of nebulae and see what's inside the nebulae, what they're made of, because I'm always talking about oxygen-3, doubly ionized oxygen. I'm always talking about ionized hydrogen, and I'm always talking about stars that have as element factories and have all the elements in their spectra, a lot of the elements. So the system that I want to get will actually allow us to show you that dynamically, and that's actually something that will go right next to this telescope in here, and it doesn't need to be a large system. In fact, it could probably ride on this telescope actually. So I'm thinking we might be doing that too pretty soon. If we get this grant, then it's sold. We're doing it. If we don't, well, it'll be longer. But we'll see what happens. If anybody has any ideas for astronomical outreach grants, love to hear them. I'm right here, ContactSkyTour@gmail.com. Or you can find us at skytourlive.org. Again, I built that site, I got that email. I mean, this is a labor of love, labor of passion. Daryl and I don't get paid for this. And I'm not looking to get paid for this. So any grant monies I get, I would never consider using for myself, because that doesn't make any sense to me. I won't further this science if I do that. So I can't do that. So that said, that's kind of where we're at right now. The other thing we're doing is we're getting together the equipment to put the solar observatory in, and that'll be out here. So STLS 3 is going to be back on the East Coast where it started to begin with. And that telescope is a solar telescope specifically for looking at prominences and solar flares and things. And I'm a big fuzzy ball. There we go. So that's the next one, and so that's all happening. So any contributions we get, any donations we get, any Patreon monies we get, any purchases through SkyTour Shop, they're all going to get better and further the amount of equipment we have. So that's pretty cool. Now, when you start going into spectrographs, we're not talking about a gradient. I mean, I have a gradient. Like, I can actually, right now, flip to the SA100 gradient right now, and you see a little spectra of the craters on the moon and so forth, okay? But that's just a gradient. That's not, it's not an actual spectrograph. A spectrograph is a tiny slit which you put over a particular star or nebula, and that slit delivers to you a lot of information about the composition of that entire area. So we're going to get what's called the low resolution version, and you might say, but why not get the high resolution version? Because it doesn't work quite that way. The low resolution version is for faint objects. So in other words, low light resolution. The high resolution is high light resolution. So things like very bright stars would work for that. And but not a planetary nebula, for instance, unless it was very bright. If we want to look at what's inside a planetary nebula and literally see all the elements that are lurking in there, this will allow us to do that, and the low res version is the best one for that. So this is a good way also, believe it or not, to look at stars and see if there are exoplanets around them, because we can look at the pollution within the spectrum with the resolution and actually see if there is a line of a spectral line in it that doesn't belong there. You know. So anyway, Kathy says, Mark, do you have the info posted on what the grants will be used for? I don't yet, Kathy. I did the application only 3 days ago, and I've already talked to them, and they seem highly interested in what we do. So I'm looking to hear back, and once I hear back, I'm going to then put out exactly what we're going to use it for, because we are a non-profit company, and all that data is available to everybody who watches, by law, and I'll do it anyway because I want to. I can't wait to share that with you. But I'm telling you now what it's for. We're also going to upgrade the infrastructure in Benson as well. We might be getting our own Starlink out there, because right now there's other buildings open out there, and I'm not noticing any slowdowns. But then again, I'm also only looking at one thing and one thing only. I'm not sending up a lot of photos and so forth. So I am not actually utilizing the full bandwidth here. It's actually a very much more simplified night than our normal nights. So I don't have to update the screens constantly because we're looking at the same thing most of the time, But we'll see what happens. So we'll see what happens. But this mount... Oh, I'm sorry, Daryl, go ahead.
Do you think the light on the Terminator behind Aristarchus has changed anymore?
It's funny you mention that, because I was just about to say, it looks like it's getting brighter here, but I don't... It's definitely changing, but I don't know if we're actually able to notice it. I'm going to increase the brightness now just a little bit and see if that...
The mountain to the right, there's a streak above it, which I don't think was visible before.
Yeah, I mentioned that before. That was there, but what's beyond it there, that wasn't visible. This part here was.
Well, that's what I'm getting at.
Okay, yeah, that's the only part that's coming in now.
Yeah.
We might be able to just really blow it out and see if it's there.
Oh yeah.
Oh yeah, see that? We might be looking at part of Schroeder's Valley here. That might be part of Schroeder's Valley. Huh. Very cool. Wow. All right. Well, so there we go. So that's some pretty cool stuff that we've done tonight. I want to actually leave that right there for a moment, and go back to the LRO map for a minute. Now, let's just look at anything else that I might have left out. Okay, there's a few other things that this LRO QuickMap does, and among them, these layers, guys, these are just absolutely incredible layers. Okay, you have, this shows you the LRO satellite where it is at the moment. This shows the different shadow cams, 3D models that you can use. I'm going to show you something else too. Those prints I told you about, well, let's just pick a crater. Alright, this one here. Alright, this crater, let's get the name. This is Borealis.
Oh, yeah.
Borealis. So if I come into our tool here, okay, this guy, and I grab this guy now, and I draw a square around this by going like this. Okay, so I got that. Now we have, inspect, we have search. Okay, there's a, and it tells you like basically, what's going on in here, etc. But if I go to other, look at this, 3D printing. Now you pick that, and you'll get the following. Okay, it's not going to do it because it's probably too big. What you end up getting is a 3D rendering of this area. And I'm thinking maybe I just have to refresh. Yeah. So we're going to refresh and try it again because I want to show you this. Let's see if this will work this time. Okay, so let's draw this again. Let's get rid of this. And of all times, now it's not working. Now it's hung. That's great. Okay, maybe it's not. It just needs some time. So let's bring this up again. Let's now delete that. Let's draw this back again. It can be temperamental sometimes, but you have to see this. I'll just do it that way. And let's see if it'll show this. If it doesn't, I'll show you next time. Okay. So here's what happens. You basically get a 3D model. And now here's the 3D model. And you set up a name. You give it a name. And this will be Borealis. I might spell that wrong. And then you can set the vertical exaggeration. Now, you can go to like 7 times, and of course that looks crazy wrong. I only go to 2 at the most. And then you're not done though, you're far from being done here. But then what you do is you say build the 3D model. Okay. And now you have this 3D model, and it will come down in the zip file. Alright, and then when you look in the zip file, which you can't see, okay, okay, this is, when you look in the zip file, what you can't see is you have the file in there, and the file is a STL file. The STL is the stereolithography file, where you can get this height data like you see in that image there. And then what you do is you take it into a program called Chitubox, ChITUBOX, or Lychee Slicer, and you can actually then prepare it for 3D printing. Now, I've got it pretty much down to a science, so I grabbed Aristarchus, and I went in, and it took me about 10 minutes to get it ready to print. And I printed it. I had it done because I've optimized my printer. I had it done in about 20 minutes, and then I took it, I cleaned it, got rid of all the resin on it because it's a resin SLA, and then I painted it. I went in, took an airbrush, and I painted it up with the right shades of color and so forth on it. So that's what you can do. That's another thing you can do. Now, it's something that I've wanted to do for a long time, but I also have a way to do it with Mars and asteroids and Pluto. I've done Pluto quite a lot, actually, and did Sputnik Planum actually, with the 3D printer there, and so forth. And that's a different application altogether. And so 3D printing is around the corner for mass consumption, to be honest. And we'll be able to do that in short order, I believe. But there you go. So that's a pretty good introduction to this product and how it'll work and how it does work. So I think that maybe you guys can take it and run with it. And remember, it's at QuickMap. Just look up QuickMap, LRO, QuickMap, all one word, QuickMap, and you'll find it. And undoubtedly some of you are doing it right now and saying, whoa. And if you have spouses, they're going to hate me, because if you're interested in the moon, this is going to take you away for hours and hours and days and weeks. Your mind is going to go through the roof on this. So LRO QuickMap is wonderful, and using it in conjunction with an actual view of the moon is again something else that we have never really done, and we're doing it now. And as the temperature drops out there, I've got to keep refocusing, which is okay. That's what you're supposed to do. I don't have my coefficients for this telescope focuser yet.
Borealis, the crater,
Yeah.
was named after Ismail Borealis, or French astronomer from the 17th century.
Wow.
Borealis is the Latinized name.
Wow. Okay. Thank you for that.
He was a cool looking dude too.
Yeah.
Yeah, heck with it. I'll post it up in the chat, the link.
Okay.
They have a picture of him in there.
By the way, look at Kepler now. We can now see the bottom of the crater at one end. We could not see that before. We just saw the kind of the illuminated edge. Now we see the bottom of the crater. So the sun is slowly rising within there. Very cool.
I won't taste.
No. Bully Aldous doesn't want you getting anywhere near him.
No doubt.
Well, this is cool, guys. All right, well, we're gonna hang up the stream tonight for now. We've been going for quite a while, I think.
There he is, Ismail Borealis. Go look when the stream is done. He's
Okay.
a neat-looking old guy. Anyway, well, thanks for having me on, Mark. And
Sure. All right, everybody. You guys have a good night. We're getting, of course, now the moon is just past the zenith. Not bad. Looks good. Yeah, let's go down here for a minute. Check this out before I go. So the south pole of the moon is down here. That's where Cabeus crater is, where they dropped in that rocket stage to hit the ice at the bottom of a crater, the potential ice, and shoot up dust mixed with potential water ice. And they did see the spectrum of water ice. So it showed that they were right. There is ice trapped in perpetually dark craters. Because you see down here, there are craters that no matter how the sun is hitting them, they never ever see the sunlight at the bottom of the crater. There's a few of those. So, cool. All right, guys, we're going to call it for tonight. Hope you enjoyed the Lunar Reconnaissance Orbiter views and the views coupled with our new Benson telescope. I did not even open the Sonoran Desert telescope at this point because I knew I was just going to be doing the moon tonight. All right. This will probably be the last stream until just past the moon, full moon, and then we're going to start going into deep space one more time. So you guys have a good night. It was so good to see you. By the way, hi JSCO. I didn't see you before. Good to see you. And check out Bully Aldous and Mr. Django. Good night, man. Rogue, good to see you. All right, guys. Well, you guys have a good night, and we will talk to you again right after the full moon. All right? See you later.
Good night, all.
Good night.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming light for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the view.